Thank you, Professor. How's everybody doing? My name is Wali Palmer. I'm ecstatic and happy to be here. These past 9 weeks has been wonderful. One heck of a journey. Um, I'm here to talk to you about my research efforts involving quantum cascades lasers, designing and optimizing an actionable laser. These lasers play a pivotal role in the advancement of technology because of their extremely and unique characteristic. These lasers have a wide range of applications. Biomedical. Their biomedical use includes non-invasive diagnostics and imaging because of their tunable mid-infrared wavelengths that can penetrate biological tissue. This includes breath analysis also that can monitor glucose levels, cancer detection, and even all sorts of abnormalities in the body that can be easily detectable with these particular lasers with accuracy and efficacy. Gas trace sensing. These lasers are widely used in gas trace sensing applications, especially for detecting gases and pollutants in the environment. Defense and security. Through the detection of chemical agents, explosives, and surveillance systems, these lasers are well suited for infrared countermeasure intelligence. Thermal imaging. Their high power output enables them to enhance image resolution and sensitivity in night vision and infrared microscopy. But this merely just cracks the surface of what these lasers can do. Now, my particular efforts involved designing my own particular laser this summer. Quantum cascade lasers basically are based on the principles of inter-subband transition of quantized states within a multiple quantum well heterostructure. Now, what does this mean? Well, inter-subband transition of quantized states just simply refers to the act of an electron transferring from one energy state to another within the same conduction band. Now, if you look here in this particular area, here, this is what you consider to be a conduction band. Hold on, I can't see this. This is way too small for me. Who got this small like this? I gotta change this. This one right here is too small.
Yep, there's a vertical line.
Hey, Max, where's that?
No, you don't.
I'm a PC guy. Okay. Well, as I was saying, this area here, this is your conduction band, right? Now, as you can see here, this green arrow here, this is an electron. The electron has to pass through this injector region right here, and then it makes a vertical transition down into what is considered the active region. This red arrow is also electron, but when it passes through the active region, it shoots off a photon, which is light. Now, this process, it takes place as many times as you can repeat the process as whatever you set it to. But how this laser transitions through the injector and the active region is where the whole idea of cascading comes from. That's where you get the title quantum cascade lasers. Now, as I said before, these lasers are based on inter-subband transitions of quantized states within a multiple quantum well heterostructure. Well, the heterostructure refers to the interface between two different types of material compositions within the quantum well. Now, okay, now we're going to the next slide. Again with the Mac. There we go. Okay. All right. Now, you'll see here, this is basically a depiction of the software that is used to basically design and simulate quantum cascade lasers. Now, you have here your materials. This is considered your barrier materials because it consists of indium and gallium and arsenide. And this here you have is considered your well layers here, which is consist of aluminum, gallium, and arsenide. Now, the difference in these two materials plays a big factor in how the design of the laser is going to interact. These here are your layers. On this particular conduction band, you have 22 layers. This is layer 1, which is your barrier layer, and this is your last layer, which is your well layer, from 1 to 22, and it repeats. The process repeats in this particular conduction band 4 times. As you see here, is set to repeat at 4. Here you have your energy field. Your energy field just basically determines the amount of electric conductivity that you want to display. Then you have your dipole, your low scattering, and your figure of marriage. All of these come down to the figure of marriage. Being able to design an effective laser all semis down to getting a great figure of marriage. Because when you have a great figure of marriage, then that tells you that you have an optimizing laser. Now, in my first model to find an actionable laser, I generated a sequence of layers based on an educated guess using the technology centered around Irvin Jr.'s tutorial. I realized that in doing that, such measures were not great. After I started studying particular literature and started extending my research, I realized that the approach I used, it made no sense at all. As you can see here, my energy states are all over the place. These little squiggly things, these are considered your energy states. There was no quantized separation between the energy states, and there was no way for me to identify a particular active region, which is usually in this area, or an ejector region. And as you can see here, my figure of marriage is at 45 picoseconds angstroms, square angstroms, which is relatively low for this particular model. So when I selected these two states here, this is the results of the calculations that the software Irvin Jr. gives you. Now, when I decided to come up with my second model, what I did was I read a bunch of literature by my faculty mentor, and I started seeing a particular pattern in how these lasers were designed using sequences within the wells and how the thicknesses of the material compositions were used. And I just came up with a system of layers that made more sense. I constructed the layers in sequential orders and descending orders, and I set my well layers. Here is particularly what they consider to be your quantum well layers. I made sure those layers were thicker than the rest of the layers. These are the active regions. These are the injector regions, where they're relatively smaller, and I did that purposely. And you can see from this particular design that up here, you have what is considered like population inversion, which is just simply when a system exists. In this case, the system is a state of energy that is taking place up in the higher region, as opposed to in the lower region is more higher than the lower. But you can see here that you have your electron transitioning here and is shooting off a photon. This is considered, the active region, as I said before. But as compared to my last laser that I did, none of that activity is taking place. And you can see the difference between the two. Not only that, my figure of marriage increased by particularly a lot, 540 picoseconds squared angstroms. So it got a whole lot better. But I wasn't satisfied with those results, so I decided to take my experiment even further. And with Model 3, I got even better results by increasing some of the barriers and decreasing some of the layers, the well layers, and decreasing my energy field by 60 kilovolts per centimeters to 54 kilovolts, I was able to come up with a whole lot better figure of merits, 1600 to be exact, picoseconds per square angstroms. That is a very well laser. And you can see the transition here. Even though it's more diagonal and it's not vertical, the transition is excellent because your figure of merits tells you this. This leads me to wonder whether the electrons will have to work harder in making that transition. But here, as you look at this right here, this calculation right here, which is your tau upper, is significantly higher than your tau lower. That means these energy states up here are significantly higher than these right here, and that's what you want. You want those to be relatively higher because it encourages this electron to make that intersubband transition. So my next model was even better. Even though my figure of merits increased only by 60 picoseconds angstrom squared, it still was significantly better by me just increasing some more barriers and decreasing some more layers and decreasing my energy field selection of these two energy states. I got a better figure of merits. But I couldn't stop there. I just kept going with it. And then in my fifth and last model, my figure of merits increased significantly, I would say, to 2,536 picoseconds angstroms. Now, I did that because what I did was I increased each layer by 5 angstroms. Angstroms is just basically the measurement of about 100 millionth of a centimeter, because we're talking about subatomic particles that you can't see with the naked eye. They're very small. And I reduced each layer by, I reduced layer 2 by 8 angstroms and reduced a couple other layers, and I gradually increased layer 10 by 10 angstroms. And I also took off 2 layers to spread out the composition of my materials. And here I got the greatest result that I could possibly think to get in this particular situation. And so I would say that with that, I came up with a way greater laser. And so if you look at the model summary of each model, my figure of merits increased significantly with each trial. But here you have the dipole. Now the dipole also decreases, which I didn't necessarily agree with, because your dipole is where if you have a smaller dipole, it could disrupt the laser activity. But in this case, my figure of merits was so high, it didn't really matter, because what that tells me, my upper tau, now that was so great in each model that I know that all my energy states within the upper part of the transition was so great that it was going to give light irregardless. And so I can say that in this whole process of me doing this and constructing these particular lasers and these designs, that I was able to come up with something that was rather actionable, something that can be probably used in all types of industrial use throughout the world. As I said before, in gas trace sensing, breath analysis, where they can just put a tube in your mouth and detect all sorts of abnormalities and things of that sort. And so in my work, this is what I particularly did. I used the software Irvin Jr. for modeling my own QC and designed a high-performing laser to maximize it to the highest possible figure of merits that I can come up with. The initial Model 1 was not a good laser, as you've seen before. It had a very low figure of merits, but my last model was very excellent. It had a high figure of merits. And if given the time, I would take Model 2 and build on it in a manner that would decrease my dipole while increasing my figure of merits. Well, that's it for me. I just want to take this time to acknowledge the people that played a big fundamental role in this whole process of this summer internship. The director of this program, Ms. Bridget. Thank you very much my brilliant faculty mentor. Thank you for being supportive and helping me out. Jill Scott. I said Jill Scott. Jill Stockwell. Sorry about that. Surratt, my boy Surratt. He's been very supportive in helping us get through this process. My day-to-day mentor, Andres, who's not here right now. Flo has been very supportive in conducting everything. And Chris has been very good at putting things together. Galen, who's not here also, he has been a good, excellent teacher at providing us computational skills. Amanda Quirk, who's also not here, she was one of the first instructors that help us through physics type teaching. And Caroline, the data analyst, very, very good instructor. And Sonali, also, who's not here, was very instrumental. All these people were very instrumental in making this process what it is. And I'd like to thank all of y'all. Thank you.